Yeah, and that's the better part, the better constructed part too.
Yeah.
Falwell Senior had that vision that he totally could step of faith out on. He totally should have planned better for the rain.
The Lord should have told me this.
I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to help us to use this time wisely, Lord. In your name I pray. Amen. So I promised to prove of this theorem. Let me do that, and we'll take your questions. Theorem 4.3.7. And what's the theorem say? It says R is a commutative ring with unity, A an ideal of R. The quotient ring, R mod A, is a field if and only if A is maximal. So R mod A field, if and only if A maximal. Again, the backdrop here is that R is a commutative ring and that A is an ideal. Now, as I recall, we already have proved this part in class, right? When was that? Wednesday, right. So what I'm probably going to do, guys, is, not that it really matters to you so much, but I'm going to post this video right after Wednesday chronologically so that people who are watching will have this proof right after the other direction. But on the other hand, I'm saying this right now so that people don't get confused because, of course, the lecture that's going to come after this is actually before this. Anyway. All right, so conversely, suppose A is a maximal ideal. We're going to pick up there. So let's suppose A is maximal ideal. What's our goal then? We wish to show that R by A, right, the quotient of R by A is in fact a field. All right? And so if A is a maximal ideal, we know what? We have see here I say, how do I know that there's an X in R which is not in A? Yeah, since A is proper subset, right? Where was that? Was that in the theorem? What was our definition of ideal? Well, we assumed that it was a proper ideal in order to say that A was maximal. All right? So it depends on the precise wording, but certainly we are assuming that A is a proper ideal. All right? Maybe I should say that in the theorem. Okay. Anyway, what's that?
If it's a maximal ideal, it has to be, right?
That's my point. Yeah, yeah. But it's probably better for me to actually say that here. Okay, anyway. So it is a proper subset of R, which means it's got some point in R which is not in A. And that's important because that's going to be non-zero in the factor ring. And so hopefully we're going to be able to show that that's something with an inverse. Right? And if we can show that for any old X like that, then that shows just what we want, which is that it's a field, right? Every non-zero thing has a multiplicative inverse. All right. So I say construct B. What is B? B is equal to XR plus A, such that what? R is in the ring, and A is in A, if I'm guessing. Am I right? Yeah, I'm right. and I claim that this is an ideal of A. Let's see if we can't prove that, right? So what do we need to prove? That we want to prove that B is an ideal of, not A, I said. I need to prove that B is an ideal of R. Let's argue. Let's explain why B is an ideal of R. What do we need to show? Okay, so let's let B be an element of B and S be an element of R, right? We'd like to show that BS is again in B, right? So B is equal to XR plus A, right? And what does that make B? Where? You know, R is in R, and A is in A. Thus, BS is equal to XRS plus AS, right? Which, by the way, is equal to XR prime plus A prime for R prime in R and A prime in A, since A is an ideal. So AS equals to A prime is an A again, right? And the fact that RS is R prime, that's just because ring multiplication is closed, right? Do you guys agree? So we've shown what? That B times S has this form, which means it's in B again. Thus, therefore, I should say BS is in B. Likewise, if we have, let's say, B1 and B2 in B, where B1 is equal to XR1 plus A1, and B2 is equal to XR2 plus A2 for R1, R2 in R, and A1, A2 in A, then what? If we look at B2 minus B1, what do we got? So sometimes I leave things as a reader, as an exercise for the reader that are actually difficult. This is not one of those cases. Like, it is pretty straightforward to show this is an ideal. We're almost there, right? We've got X times R2 minus R1 plus A2 minus A1. And, you know, this is in R. This is in A again, because A is an ideal. It's closed under subtraction. So we've shown that the difference of things in B, what is it?
Why are we showing the difference?
Oh.
I thought for the ideal we just had to show the multiplication. Like, that's what I have written down in my notes. I don't have the subtraction, so I don't know what we're doing.
Oh, okay. Let me check on that. It is possible. It's that time of day, Friday, that I...
Well, one of the definitions of an ideal is that it's a subroom. So do we have to prove that it's a subroom before proving that it's an ideal?
Well, let's give me a second here. I'll go back. Theorem 4.22 is what I'm using. So Theorem 4.22 tells us that a non-empty subset A of a ring R is an ideal of R if, whenever we take two elements of the subset, the difference is in the subset again, and also part 2, which is the Uber closure. So that's what I was thinking of using. Now, the context of what you're remembering is The definition starts with the assumption that A is a subrung, which contains within it the assumption that it's closed under differences. Yeah. Oh, well, it's commutative. This is commutative. R is a commutative ring, so we only need to show one of the closures. You don't need to do both. Which you may recall as a follow-up comment to that theorem 4.22 when I put that on the board. I was like, oh, and if it's commutative, we just need to check either one or the other, right? Or you could just write an extra half sentence and say, therefore, SB equals to BS is in B. I mean, whatever. So anyway, there you go. Thus, B is an ideal. Now what's left? Oh, now I've lost my place. You guys tricking me. Very sneaky. Let's see here. All right. What's up next? If A is an A, all right. Now, I need to somehow use the maximality, right? So how does B and A fit? How do B and A fit together? I'm going to erase. So you guys agree that B is an ideal. I'm going to erase that part now. I will replace it with the following proof. B is an ideal. Okay, now observe that x times 0 plus a equals to a as an element of B for each a and a, right? Therefore, A is a subset of B. But A is maximal. B is equal to R by maximality. Now that's not quite. I don't quite have I'm sorry. I don't have that yet. I've jumped the gun. What do I have to do before I can conclude B is equal to R? I better check to show that B is not a subset of A. I mean, if I had B as a subset of A, then I'd have A equals to B. That's allowed, right? I need to show why is A not equal to B? Notice that x times 1 plus 0 equals to x is an element of B, right? And x is not an element of A by construction, right? So therefore, A is not equal to B, and that implies that B is equal to R by maximality of A. Right? Okay. So now we have that this ideal B is in fact everything, right? And what can we do with that? So 1 is in B, right? So B equals to R implies that 1 is in B, which implies that 1 is equal to XR plus A for some, what? R and R, and A and A. Or if you like, I think in my proof I might have used, oh no, I did. I might sometimes use like a Y there or something instead of an R, but anyway, whatever. So the larger point is this tells me that 1 plus A is equal to X plus A times R plus A, right? So therefore X plus A inverse is equal to R plus A for X plus A in R by A. But that was an arbitrary non-zero coset in the factor ring, which we just showed has a multiplicative inverse. And do we also know that the factor ring is a commutative ring with identity? We do. So that shows it's a field, right? Because it's a commutative, R mod A is a commutative ring with unity where every non-zero element has a multiplicative inverse. So I think in here I'm still reiterating some of the facts about coset multiplication in the proof, right? In the case you didn't already know how cosets multiply. But just to get to the point, it's on the board. All right, well that's it. So took me longer than I thought. Good. I didn't keep you guys after class to do this, my goodness. We'd have been here till Dr. Sprano started, practically. Actually, okay, it wasn't that bad. It was just 15 minutes. I thought I could do it in 10. I was wrong. It's probably your guys. It's probably your fault. I blame Bethany. No, I blame Morgan. Okay, that's okay. Can I erase? Anyway, the more important thing here is to remember the result, actually. If we have the quotient by an ideal is a field, then that shows you that the ideal is maximal, and vice versa. Very nice result. So any questions, you guys? No questions? Does that mean I can go home? The picture, oh.
Yeah, because I saw the example that was like pink equals something, and like that.
You say, I saw the example, as in speaking of yourself. I saw it.
She wants to look at the picture.
Okay, yeah, we can start. We can talk about this example. I'll start from the beginning. So here we're looking at the ring of Gaussian integers. So the Gaussian integers are especially interesting because they allow you to study number theory with abstract algebra, among other things. So what are the Gaussian integers to start with? They're z adjoin I. They're things of the form a plus bi such that a and b are integers. That's the so-called Gaussian integers. Sure.
In general, what is that notation? Like if it's not I, how do you know that it's like a plus b times something? How do you know it's not like a plus b times something plus b times something? It's like the adjoin notation, I guess.
Well, I mean, let's see here. Another use of this notation. So this is a plus b root 2, a and b rational numbers. How do I know it's not? Your question is, how do you know it's not?
So like, what if, is it possible to have two things in the square bracket, and then it would be like a plus b times the first thing plus b times the second thing? Or is it
Yeah. So, indeedly doodly, you could talk about our, I don't know, Sure. So for example, R adjoin I and J would probably be things of the form A plus BI plus CJ. I think that's, and then maybe plus DIJ. Or you could talk about Q adjoin the square root of 2 and the square root of 3. But I don't know, I'm a little fuzzy here at the moment. Usually when I start thinking about these things, I'm thinking about fields, not just rings. So I'm worried I'm misstating something at the moment. But that is what it means. I guess I would say this, it's in some sense consistent with the polynomial notation, right? Because when we write, yeah, Morgan? Oh,
This is the standard I that we usually work
yeah,
with.
right.
And how is that different from the complex numbers?
Oh, because it's just the grid. We could be here all day. This is 4 plus 4i, I, 2i, 3, oops, 3i. Yeah. 4 plus 2i. So it's the lattice, it's a grid in the complex plane. But yes, it is true that the universe in which the Gaussian integers lives, we could think of it as a subset of the complex numbers, which is nice because then we're...
I think the x-axis should also be.
Oh, sorry. But yeah, I endorse your modification of my picture, but there, now I fixed it. And anything else I've done? Okay, it's that time of the day. Now, but the larger, so it's not a terribly, like when I taught abstract number theory, when I taught number theory, I didn't feel bad about using these because it doesn't really require abstract algebra. I mean, these are just particular kinds of complex numbers and you can study their properties. All right, Gaussian integers. The more difficult question you could have asked Bethany would be, what do you mean by integer in general? And that's a harder question. But, and I'm not going to answer that because I asked it first. So let's see here. So consider the Gaussian integers, z adjoin I. And we can think about the principal ideal 2 minus I. So what's 2 minus I look like? It's the ideal generated by 2 minus I. Yes, yeah. That is true. But what does that mean here? That means 2 minus I times what? Times A plus IB, right? Such that A and B are integers. In other words, it's arbitrary Gaussian integer multiples of 2 minus I. Now multiply that out, what you got? You've got yourself 2a plus b, right? Plus I times what? 2b minus a. And you can think about different values for a and b. So what does that tell us, among other things? I mean, I guess... you can think about different choices of A and let's just try to think about different choices of A and B and where those go. Yeah? So here's my A, here's my B, here's my 2A plus B plus I times 2B minus A. Let's just plug in some numbers and see where it takes us, right? First of all, we could plug in 0, 0. What's that to give us? It gives us 0. What if we plug in 1 for A and 0 for B? What's that give us? if you go back up to here, it better give us 2 minus I, right? And what if we put in 0 for A and 1 for B? I think it better be 1 plus 2I, right? What if we put 1 and 1? 1 of A and 1 of B. What would that give us? 3 plus I, okay. So these are, what we're looking at here, these are all just different representatives of the principal ideal. Well, these are all elements of the principal ideal, they're not representatives, I should say. I mean, 2 minus I includes this set, right? 0, 2 minus I, 1 plus 2I, 3 plus I. Is there anything else we could pick close to 0? What if we graph these? What would they look like? We've got 0, right? Let's say 1, 2, 3, minus 1. So I've got the 0, 0 point. I've got over 2 down 1, right? And then what else do I got? Over 3 up 1. One plus two, I got this one here, right? What if we looked at 1 plus 2 minus I? So you just add 1 to each thing in the set, right? And so like that, I have this point, right? 3 minus I, so that point. And then 4 over here. 2 plus 2I, so it's like here. And then we could look at like 2 plus that. What would that give us? If you do enough of these, you'll see that you filled out all the grid, yeah? So I've got 2. I've got, 4 minus I, which is like over here. We've got 3 plus 2I, which is like up here. It's probably helpful to add another one. What if we looked at, so what's the rule? How can I stay inside the pink set? I'm allowed to do what? I'm allowed to add or subtract anything in the black, because that's not changing, right? If I add anything in the black, I still have this coset. So, I don't know. Why don't we, let's see here. I want to get something like over here. So I should probably just subtract 2 minus I from like 3 plus 2I minus 2 minus I. What's that give me? 1 plus I? No, 1 plus 3I, yeah? So 1 plus 3I up here. You can start to see they're always like, right, I think there should be another one here too, right? This one should be pink, shouldn't it? All right. And I think if I understand the pattern correctly, there's one here. And there should be one here. All right, let's look at the next one, which would be what? 3 plus 2 minus I, which would be what? What's 3 plus 2 minus I? I would have a 3, 5 minus I, 4 plus 2I, 6 plus I. Those are not really on my picture, right? The one that's on my picture is the 3. Can I picture any of the other ones? 1, 2, 3, 4. Well, it's here. Fine, there. I think this should be green, right? This one? Right here? That one? Now let's check. That would be 1, 2, 2 plus 1, 2, 3, 2 plus 3i. Is 2 plus 3i plus the 2 minus I equal to, 3 plus 2 minus I? That means that 3 minus 2 plus 3i, which is equal to 1 minus 3i, is an element of 2 minus I. Is that the case? Maybe. I don't know. How would I get to 1 minus 3i? If I subtract this one from that one, right? You can see that, in fact, 1 minus 3i is, again, another thing in there. 1 minus 3i, so there's another, that's the point I'm talking about, that's in there, which I think is consistent with the general pattern here. What color, is this a green? I think that's a green, right? So I think we're missing something though, right? What are we missing? You see what we're missing? We're missing this one here, right? This one here, and then down here, and so forth, right? So what is this missing coset? Well, I think you can see what it is. The remaining one is 1, 2, 3, 4, plus that. And if you did this carefully, you could see with the fifth coset that we've got to, we've covered everything in the Gaussian integers. Everything fits into one of these five cases. I used blue for 2 minus I used green for 1 plus 2 minus I used red for 2, yellow for 2. Oh, I did a different thing. I used 2 plus I instead of, but 2 plus I is actually minus 1, which I think is the same as what? In my current color scheme. If I go to minus 1, isn't that? That's brown again, isn't it? So I think that yellow is my current brown, and pink is my current green. So if we turn the page here, we get this. And what I'm picturing there is that the cosets in the Gaussian integers divide the Gaussian integers up into these 5 classes, right? So if we look at the factor group, we could look at Gaussian integers mod the principal ideal generated by 2 minus a. What would that give me? Right, what's z join I mod the principal ideal generated by 2 minus I? It's isomorphic to something with 5 things in it, right? I'm pretty sure it's isomorphic to z5. Ooh, I don't claim that in the notes, and I don't think I show it either. If I was right, if this is isomorphic to z5, what should we be able to see? z5 has got what in it? 0, 1, 2, 3, and 4, right? And that's generated by what? So we could either generate it by 1 or by, oh, it's z5. So all of them. So let's see here. That says then that it should be possible to generate all of the ideals, if I'm right. If we pick any one except for A, and we look at powers. So like, for example, if I take, let's look at 3 minus I plus, and if you don't mind, I'm going to call the ideal J. Let's let J equal to the principal ideal generated by 2 minus I, because otherwise I'm getting really tired of writing that. So how about 3 minus I times J? What happens if we square this? We get 3 minus I squared. What's 3 minus I squared? It's 1 plus 2 minus I squared, right? Am I right? And the reason I would do that is then that's 1 plus 2 minus I times 2, right? Plus 2 minus I squared plus J. But you see, what's the rule for J? J sucks in things like this. They just get eaten in there, and then you got yourself 1 plus J. Oh man. Oh, I'm an idiot. What should 1 times 1 be? 1? All right, so I think I've just discovered that this is 1 plus J, yeah? So like 1 plus J squared is 1 plus J, yeah? Okay, great. Look, 3 minus I is in, remember we've talked about this before, 1 plus the coset is the multiplicative identity. How should I generate things in Z5 anyway? Additively or multiplicatively? What? Additively, yeah. So I'm doing the wrong thing altogether. I just, it's Friday afternoon. You guys can't trust me. I don't know why you come to this help session, honestly. Let's try this again. What if we try to, say, add 1 to itself? 1 plus, oh, you can see that pretty easily. 1 plus J plus 1 plus J is what? It's 2 plus J, right? And then if we do 3 times 1 plus J, we get 3 plus J. If we do 4 times 1 plus J, what do we get? We get 4 plus J. And you know that J, 1 plus J, 2 plus J, 3 plus J, and 4 plus J are distinct, right? We've learned that in our analysis over here, right? We looked at the the ideal, 1 plus the ideal, 2 plus the ideal, 3 plus the ideal, 4 plus the ideal, 4 plus the ideal, and those were the distinct red, black, blue, pink, green, and brown grids. So those are distinct. What happens though when you do 5, when you add 5, what happens when we get to 5? What's 5? 5 times 1 plus j is what? That's 5 plus j, and that is equal to j again. Why is 5 plus j equal to j again? So my question to you is, what's that? That's what I'm claiming. I'm claiming that the Gaussian integers mod the principal ideal is isomorphic to Z5. That means, if I'm right, that the 1 in the factor ring should have order 5 additively. Because 1 in Z5 has order 5, right? We should be able to prove that the factor ring has characteristic 5. Yes, that's it. It's the 2 minus I times 2 plus I is equal to 5. So that means 5 is an element of this guy, which is to say that 5 is 0 in the factor ring quotiented by j, formed by quotienting by j. Now, not everybody looks at this graphically. Like if you read Gaussian, he doesn't have this picture or anything. He just does hand-to-hand combat on the equations and stuff. But I found these pictures to be very helpful for me. Anyway, you guys have questions? So it was already in the notes when I covered it before, but the way to see the quotient by x squared plus 1 properly is just to look at the division algorithm, right? If I divide by x squared plus 1, I can pick, it gives me a q of x, an x squared plus 1, and a remainder term which has degree less than that. The remainder then has the form mx plus b, or ax plus b if you like, and so then we get f of x plus that is equal to ax plus b plus that, which means I can always choose the representative just to be a linear term. So I said that in class. I didn't really prove it this way, though. Yep.
So in this example, you had said that you can basically treat x squared as negative 1.
Mm-hmm.
Is there a same idea here, or is it different because there isn't a power of I?
So your question is, this Gaussian integer business you're doing, could you construct it by a polynomial quotient? Right?
Sure.
And the answer is yes. So we could say, really, that z adjoin I is isomorphic to z adjoin x quotient by the ideal generated by x squared plus 1. So, yeah. This would, for pretty much the same argument, the real coefficients here, if you study this argument, I don't think we really need the structure of the real numbers. Is the division algorithm defined for polynomials with integer coefficients? Question, isn't it? Well, if it is, then we can make that step, right? And we can find the remainder. So we can view this as a plus bx, right? Such that, a plus bx plus this thing, right? Such that a and b are integers. And then the thing is, if you take a plus bx and you multiply it by c plus dx, goodness gracious, plus the x squared plus 1. then we multiply representatives, right? So we've got AC plus BDX squared plus AD plus BC times X plus this thing, right? You wasted my time enough. Oh well. And then this thing, right? But you see the rules. See, I just added 0 in a way which was conductive to my thought process, which is now I've got x squared plus 1 times this, which just gets sucked into there, you know, because we can eat things inside the coset into the coset. And we're just left with AC minus BD plus AD plus BC times X plus the coset, yeah.
Do you have to do the 0 or like is it bad notation to just substitute -1 for x squared?
Well, we shouldn't really say I mean, it's not true that x squared is equal to -1. What's true is that x squared plus this coset is equal to -1 plus the coset, right? So if you let x bar equal to x plus, you know, x squared plus 1, yeah? And if you let, I don't know, c bar equal to c plus x squared plus 1, then this stuff looks easier, right? So then in that case, we do have x bar squared equals to -1 bar. But that's just a way of suppressing the cosets explicitly. Now, what's the isomorphism? Between this factor ring and the Gaussian integers. It's defined by psi of I equal to what? I mean, if you want, I can be less sneaky. So psi of A plus BI equals to what? You just do A plus BX plus the coset, yeah? Or you could just put a bar over it if you want to use my lazier notation. But yeah. So if we adjoin, in contrast, if you just look at like z of x, this is unending because that's just polynomials with integer coefficients, right? There's no condition on x. X is what you'd call an indeterminate. So, and the difference between indeterminate and variable is somewhat philosophical, but more or less, indeterminate, we're not actually thinking about x taking a value. When we talk about polynomials with integer coefficients, we're not really talking about functions. We're talking about expressions with polynomial coefficients. Now, it is true that those correspond to functions, but we're not actually thinking about plugging in things to x. Or one thing. We could think about plugging lots of different things into x. Yeah. That's actually Monday. So, do you guys have other questions? What mission are you guys on right now? 6. Let's look at mission 7. Sure, why not? Do you guys got questions about mission 6? I guess we could do that. Let's see here. See if I have anything. Do I have anything to? So, problem 51.
Let's talk about it.
Problem 51, for those of you who are not here and do care, it's important to look at the sum of things. If you do not use the distributive property of a ring, you'll never get it. Problem 52, if you are thinking about this for longer than a half hour, you need to stop, come back and think again. Before you think about it, you should understand that words in this problem mean things, like integral domain means something. If you don't know what that means, you cannot do this problem. It has been rumored to me that it's hard to see where using d square free actually figures into any of this. I'm inclined to agree with that.
I started looking at that question.
Yeah.
I think I know why.
Oh, you do?
Possibly.
Tell me.
Because I'm pretty sure that you have like a squared minus d times b squared or something. If it's not square free, that can be 0.
Oh. So the reciprocal formula might be,
I didn't finish it,
well,
so I'm not really sure.
but I feel like if d is, all right, well, I don't know. I'm not entirely convinced that square free has anything to do with anything there. I'll just say that. I'm not convinced at the moment. Problem 54, the way to solve this problem, what you should be doing is you should be checking every single property that the alleged addition and multiplication satisfy. So it's important to like figure out what's the additive identity, what's the multiplicative identity, are they associative, right? Is the addition commutative, right? Is there an additive inverse? Do you have to check for multiplicative inverse? No, we don't. It's a ring, right? That's not assumed. There should be a multiplicative identity, though. I mentioned that already. I'm in reruns. I will spoil it for you and tell you that it is, in fact, not a ring. So I'm not going to tell you what breaks down, though. That's up for you to find out. Although if you pay Emily some unknown amount of money, she might tell you. What's that?
I said, how much money?
How much is it worth, Emily? Is it like, is it worth it? Is it worth $1? Is it worth, I don't know, 50 cents? I mean, what's it?
Depends on the level of friendship.
Maybe a cookie, a cup of coffee? I don't know.
I hate
Um,
coffee.
Oh, you hate?
No.
Oh. So they could drink coffee that was given to you, if that was a situation you were in. No, okay.
You just don't like it? Like what it is?
No.
Do you like tea?
Yes.
Ah.
Stand coffee.
Oh, sad.
It's awful.
This problem 55, I don't know. There may be slicker, snazzier ways to do it, but the way I worked on this with Emily, I think it was you, Emily,
Yeah.
and we basically just made a table with 16 values and studied the possibilities, and we found that some of them had multiplicative inverses and some didn't. If you look at the condition, if you just try to solve, just what does it mean to have an inverse? Now, again, I may be forgetting some kind of slick abstract algebra way to do this, but if you're trying to solve a plus ib times x plus iy equals to 1, this has to have a solution. That would make this a plus ib inverse, right? If such an x and y exist. And when you multiply that out and look at what you've got 2 equations and 2 unknowns in Z4. They're linear, and so you can use the 2 by 2 Z4 inverse formula as it makes sense or doesn't make sense. I mean, you can study it from that angle. There's a lot of different ways you could look at this, but I think a case-by-case analysis is needed. And we did find that there were quite a few units. But there's also, it's not a field. There are definitely 0 divisors, right? So a healthy thing to do, for each thing you think is a 0 divisor, show that it is. do you remember which one we found was a zero divisor, Emily? Just for me to make that comment, make more.
Which one was it? Like, an example of the
Just
value?
yeah, just an example of a zero divisor in Z4i. What did we find? Which one was it? I'm just looking for something that's not a unit and not zero.
Not a unit. Oh, that would be 2 then.
2?
Yes.
So 2 times something is equal to 0, and yet that something is non-zero. What would that something be? Oh, how about 2? Yeah. So there you go. There's 1. This was not especially exciting, but you can also see that 2 plus 2i is also a troublemaker, because that's also a multiple of 4, which is 0. This is, okay, so there's 2 things which are not in the group of units, but you got to sort through it. There's 16 cases. I recommend a tabular method. Have I told them enough?
If you
Okay.
like 16 things this way and 16 things this
Well,
way.
I-
No, like here.
A
Oh, God.
A is one column, B is the other column, but A and B are taking 4 values, so you got 16 rows. Okay. Problem 56. Problem 56, you probably would be wise to think about the first isomorphism theorem. Yep. And I think the
Dr. Cook, do we ever cover the second isomorphism theorem?
you want me to cover the second isomorphism theorem?
I'm just asking if we do.
Can I also
In abstract too.
can I also cover the third and the fourth?
I don't care. I was just wondering if we did an abstract too.
I will in abstract 2 if I don't get to it in abstract 1.
How many do we cover in abstract 2?
There are 4 popular ones.
But do we cover all of them in abstract?
Yeah, I mean, I think so. Yeah.
First one is simple.
I went through the videos and it didn't say if it said second isomorphism theorem, so I was like, oh, maybe not.
Well, the second and the third may one or both of those may have already be homework problems that you've had. I don't know. I mean, proving the second or third isomorphism theorem are decent test questions for you guys. For example,
We're going to talk about what they are before that.
doesn't matter. Doesn't matter. The fourth isomorphism theorem, or the lattice isomorphism theorem, is quite beautiful. It says something about taking the lattice of subgroups for a group and then finding the lattice of subgroups for a quotient of that group by just taking the original lattice and just like crossing out stuff below the normal subgroup which you're quotienting by. It's really cool. But anyway, next semester probably for that one. I have covered it during the semester and previous semesters, but those were semesters where I didn't also cover matrix groups. Right, so the net difficulty is conserved, which means I'm going to spend our intellectual capital on the matrix groups this semester and not the lattice isomorphism. Now, listen, if F is the kernel of the isomorphism is what? I mean, we can use the first isomorphism theorem. If F is a homomorphism of rings, then the kernel is, I mean, psi is a homomorphism of rings. The kernel of psi is a ideal. It's an ideal of F. Right? So, I can't say much more about that, otherwise I'm going to solve it. That one's, subring test, pretty cut and dried. This one here is, I think, also pretty computational, nice, and should be fun. First isomorphism.